Hello everybody, I'm Tom Poole, and today I'm going to talk to you a bit about some alternate std function implementations. So the main motivation for this work is, or at least the main motivation for this talk is some work I did a while ago, which was adding a std function replacement to the JUCE framework, which is an open source cross-platform effort. And I'm not just saying that to name drop the product that I'm working on. There are a couple of aspects of JUCE that means that a std function replacement is kind of uniquely valuable. And these two things are that JUCE has quite broad cross-platform compatibility requirements. And it's also focused on audio applications. So we'll get to those two in a minute. But first, it's worth just giving a quick std function recap. So in a single sentence, std function is a type erasing wrapper that holds something that is callable with a specific signature. And so the things that are callable in C++ are function pointers, objects with a call operator, and lambda functions. And just a quick example of each of these on the left-hand side. We have a function, we have some struct which has an invocation operator so we can call it, and down the bottom we have a lambda function. And each of these can be assigned to a std function, and that's good because we can treat them all on an equal footing. So why is that useful? I think it's fair to say that std function really has changed the way a lot of programs are written. Actually, not programs in their entirety, but certainly bits of them. If you're interacting with anything that is asynchronous, before the advent of std function, the typical approach is that you'd call an asynchronous function, and you'd have to provide it with a function pointer and maybe sort of like some void star data to then get control back to when you started from. And the basic process would be you'd save your this pointer into the void star data. Then when you get a callback, because your asynchronous function has either finished or it's hit an error or something, you then cast this void star pointer back to an instance of yourself, and you're back where you start from. You can monkey around with all your internal data again. With std function, you can simply put this in the capture lifts, and everything is much more contained. You don't have these global functions littering your code base, where the only point of them is to get you back where you started from. And std function is also a really good fit for a lot of audio processing operations, which brings us back into why it's useful for JUCE. So you can think of almost all audio effects as being successive transformations on arrays of audio samples. So each of these transformations has the same signature. You have some input samples, you do something with it, and then your output is the output samples. And because all these transformations have the same signature, swappable arrays of callable objects is a really convenient structure that you can use to have a way of changing behavior dynamically. Or another example would be something like an oscillator class. So an oscillator class does something periodic, and a user can provide a std function to determine what the wave function would look like in that periodic bit, which is then swappable at runtime. So std function is really useful, and people who use JUCE have been using it to get things done. And so this is important because JUCE supports a lot of systems, and as you get really old on the desktop side or really weird on the embedded side, and you run into situations where actually the standard library lacking a std function is a reasonably common occurrence. Particularly in the toolchains for embedded systems, you might lack a std function, a std library altogether, or it'd be made by someone who's much more concerned with constraining it in terms of size rather than having all the functionality available. And also, if you want to target OS X older than 10.7, you'll find that you're free to use a really modern compiler, but you're limited to the standard library that's available on that platform, which gives us most of C++11, but std function is the real standout that the JUCE users really wanted. And the other aspect of why std function is particularly important when you're working with audio, using the JUCE, is that JUCE works with audio, and processing live audio is extremely unforgiving. So the process of dealing with audio starts out with you do some communication with the audio device in your system to say, okay, you tell it that I want to do something with audio, and you do that by supplying it with a callback. And this callback has, at least in its arguments, a pointer to some memory and a size. Once you've told the audio device about this, at some point in the future, it's going to call that callback. And once it's done that, you have a short window of time where you fill that block of memory with some audio data. And then a short time after that, that memory will be read by the sound card. The crucial thing here is that if you don't finish writing to that memory, you will hear a glitch. This is not really like graphics applications where you're just blasting frames to the screen. If you drop a frame, unless you're looking out for it, you probably won't notice. But if you drop a single sample, you will hear it, and it will sound terrible. And so why is that bad? Well, if your audio software produces glitches, then people will not buy it. And this is not particularly because musicians are fickle or anything like that, but if you're broadcasting live, or even doing something quasi-live, like recording a once-in-a-lifetime take, if your audio glitches during that, the whole recording is effectively ruined. And even worse, if you are doing your bit of audio processing towards the end of a signal chain on a really loud sound system, then you can actually cause permanent hearing damage to anyone listening to it. And so because of that, there really is one golden rule of audio programming, and it is, if you're working on the audio thread, you do not do anything where you don't know ahead of time exactly how long it's going to take. And if you're looking at audio thread code, two things stand out as big red flags. The first is any locks, and the second is any memory allocation. So locks are bad because, well, on this MacBook at least, the audio thread has a higher priority than any other. So as a programmer, you cannot create another thread that has the same priority. If you're locking, it is almost certainly because you want to communicate with another thread. And as soon as that thread is locked by a lower priority thread, you have effectively demoted the priority of the audio thread to the one that is sharing the lock. And as soon as you do that, the OS can just decide not to schedule that thread for whatever reason, and suddenly you miss your deadline, you hear a glitch. And memory allocations are bad, first and foremost, because they take quite a long time, and we're generally working in a very time-constrained domain. We want everything to happen as fast as possible. But the really nasty thing about them is that it can take an unpredictable amount of time. So every now and again, your fetch from main memory will take much longer than it used to, and this again can push you over your deadline, and you hear a glitch. Why is this a problem when you're working with std function? Well, std function allocates sometimes. We'll talk about this a little later in the talk, but std function can avoid allocations by using a small bit of stack space in each object. It's called small buffer optimization, and the same principle, the same thing happens in std string. So if the thing you are storing in your std function is smaller than this stack space, then the stack space will be used, you won't have an allocation. If it's bigger than that stack space, then we need to fetch some memory from the heap to hold it. And the annoying thing is that the size of the stack space is implementation defined. So short of going and reading the code in the standard library that you're using, there's no way to tell ahead of time what this stack size is going to be. And if you're going to compile the same code with different compilers, then all bets are off. We are not the only people worried about these similar concerns. So the Game Dev and Low Latency Working Group has something called in-place function. So in-place function is a std function alternative that is guaranteed that it will never allocate. It essentially uses this small buffer for everything. And that's the direction that this talk is going to go in. But also, whilst we're kicking std function, Facebook's Folly library has a couple of other improvements. First off, it is a move-only alternative. And I think this makes a lot of sense. If you think about how you use std function, it is almost always to define some functionality in one place and then pass it off somewhere else. If you're just going to define something and use it, you can use a Lambda function. It would be much more efficient. And it's very rare that you really want to copy the functionality that you've defined. And the other thing it also addresses is the fact that it is very easy to violate const correctness using std function. So std function's call operator is marked as const. So if someone gives you a const reference to a std function, you can invoke something. However, once you've invoked that something is free to modify its own internals. And as soon as you do that, all guarantees about const correctnesses are out of the window. Your compiler will not be able to help you. So let's dive in. And so what do we need if we're going to implement std function? At the very high level, we have a function class that is a template. And once we know what the types of the things that it takes as arguments and the type of the thing that it produces as a result, we can specialize that template. Note that here we don't have any information about the type of the thing that this function is going to hold. It's just the signature. So we're going to do some type erasing. This is the approach that libstd C++ uses, and it's a set of type erased function pointers. So on the left-hand side here, you can see that we have some type erased storage, just an array of characters. And we have some function pointers, where the types of all these function pointers is a sea of voids, void stars, results type, and your arguments. And in tandem with this, you have a set of type-aware functions. Now, these functions are type-aware because they have a template type, and this functor is going to be the type of the thing that we're storing. And so because we know this type, we can invoke the thing, we can copy construct this thing into a specific destination, and we can destroy it. So the constructor is where all the action happens, because this is the only place in the entire class where we actually know the type of the thing that we are going to wrap. And once we know that, we produce some specializations of each of those type-aware functions. And when the compiler sees this, it's going to go and stamp that out somewhere. We've got a pointer to it. We simply cast this type-aware pointer down into our type-erased pointers. And then we're free to use them. So in the constructor, we give it an address of the storage we're using, same with the destructor, and same with the invoke. These are all just operating on type-aware memory, but these type-erased pointers are actually pointing to type-aware functions. So that's the nuts and bolts of how this thing actually operates. But to make something useful, we want to put these things in containers. There's no point making a type-erased thing if we can't treat all of the things that we're contained on the same footing. So for that, there's not too much interesting here. We just note that we now need to know the storage size as well, because if we're assigning from a different function, we need to know the size of the thing that it contains so we can make our internal storage large enough to take it. So we've done all that. We want to know how this thing is going to perform. So we've got a very simple benchmark here. With templated on this function type is going to first be a std function, and then it's going to be our replacement. We have an array of these things in their default state. For each one of them, we're going to assign it to be a function pointer, and then we're just going to loop over them all again and produce a sum. And so we see how we did. Pretty terribly. So this guy in the greeny blue is std function, and the other side is our alternate. But this shouldn't be too much of a surprise. If we jump back a couple of slides, then we can see every time we're calling a constructor, or every time we're doing an assignment, we're having to reallocate our internal storage. And calling out to main memory is very slow. So the fact that std function is beating us comprehensively isn't much of a surprise. So how is it doing this? Well, as I previously mentioned, if the thing that you are storing is small, and in this case we're just storing a function pointer, then Std function is free to avoid an allocation by storing this directly in some stack space in itself. It's annoying because this has a non-configurable implementation defined size, but if we're going to be building a replacement for std function, we want something that operates similarly, so our users are not going to be surprised. And it's pretty easy to add in. Don't worry about reading most of that. It's not particularly interesting. The interesting bits are down here, where we have some stack space. If you haven't seen std aligned storage before, it's essentially a very thin wrapper around an array of characters. It's nicer than an array of characters because it has some sane defaults for alignment on the platform that you're running on. And it makes more like semantic sense. You don't need an array of characters. You're not going to print it. You're not going to read it. This gives you more a generic storage type, which just more clearly indicates this is just an area of stack that we want to use. And we have an extra storage pointer here, and this storage pointer is either going to be null for the default state, it's going to point to the heap if we're exceeding our stack size, or it's going to point into ourselves to the stack. And so you see in the constructor, if the size of our functor is small enough, we use our internal storage. If it's too big, we use our external storage. And you can see on the right-hand side that this, there's nothing difficult going on here, but you can see the increase in complexity of this function when we have to decide where we're going to store our internals. This could be dried, so this is essentially the destructor, and you could write this in terms of a swap function. But I just wanted to really list all the operations that you would need to do to make this work. So if we benchmark this against std function, then we're doing more or less all right. We're a little bit slower, but we haven't put any effort into optimizing this whatsoever. So again, that is not surprising at all. So if we look at the size of look at the size of our alternative implementation, we can see we're pretty chunky. We have 3 function pointers, we've got some stack space, we've got an int for the heap size, and we have an extra pointer as well. Now, if you look at the libstd C++ implementation, it deals with this in a much more clever way. So the invoke pointer is in a union with the stack. The create pointer, destroy pointer, and some other functionality are all bundled into a type arrays management function, which does all of those operations. It just takes an extra argument, which is effectively an opcode telling it what it needs to do. And the heap size and the storage pointer are all abstracted away. But we're not going to do that. We're just going to take a step back. And if we look at what this code is doing, we have effectively written our own vtable. A much nicer way to deal with this is just to use a vtable. So this is how most people are more comfortable with doing type erasure. So on the left-hand side, we have a base class, a type arrays base class, which is doing a similar kind of thing. So we have an invocation operator, and we have a couple of methods for copying memory around. And we have a derived class that actually holds a concrete implementation of the thing that we're trying to wrap, this functor here. And we have one of that. Dealing with it is very easy. We can just call it or copy Constructor into certain places. And actually, the internals of our overall function wrapper are then much more simple. We just have some stack space, and we have this function pointer, this base class function pointer, which again is either going to point onto the heap or into ourselves. And if we do this, then we effectively recover. With no extra effort, we've ended up being exactly the same performance as the std function. This is the std function from libcpp, if anyone's interested. So now we have a std function replacement that is working at the same speed. What are we going to do with it? So this is the point where someone may throw a spear out of the audience, and I have to dodge it, because adding declarations to the std namespace is undefined behavior. But we've done it anyway. No, I could hear that. So this is dangerous because there's an unfortunate coupling between the stud namespace and the compilers. The compilers are free to look inside there, and if it sees something called stud function, it at least reserves the right to make assumptions about the memory layout or how you operate with this thing. So we have taken some precautions. So we have a whole sea of preprocessor checks to make sure that we are running on a platform that doesn't already have a stud function. So some other things that work in our favor is that JUCE is distributed as source code. So whilst it's perfectly possible to compile JUCE as something like a DLL and try and pass one of these things into it or out of it, if you're on a system which doesn't otherwise know about stud function, it's very difficult to know what you're going to do with it on the other side. And because of this, it's been out in the wild for a couple of years. We've had no ABI issues or any other that we know about. So that's all well and good, but it hasn't really solved the problem of this allocation and being safe to use on an audio thread. And this is the simplest way of solving that problem. All we do is, when we construct one of these things, if the size of the thing that we want to wrap is greater than the size of the stack, we will just fail to compile. This gives us a real cast iron guarantee that when you use one of these things, it's not going to allocate. And another benefit of doing this is that the internals of all our things like copy constructor or assignments become much more simple. Because we don't need to worry about where our internal functor is stored, like it could be on the heap or it could be on the stack. Now it is always on the stack. There's much less branching. What this translates to is that actually we can get a pretty significant speed up over stud function. So this, again, this is a pretty targeted benchmark. So you're unlikely to see a 30% speed increase just from switching to this, but nevertheless, it is a bit, it's notable. So we can do that, and we can get a bit of extra runtime performance. But in terms of our memory management, we're now doing terribly. So there's a pretty good argument to making your stud function replacements have a total size of either 32 or 64 bits. So it lines up nicely with the cache lines on typical systems that JUCE users use. But if you do that, particularly if you make it 64 bytes, and you only store function pointers into it, most of that stack space is going to be unused. So the typical way of getting out of this jam, there's something that stud vector use is just you add the ability to plug an allocator into things. And when you do that, you effectively delegate your allocation behavior to the allocator. So pre-C++11 allocators were extremely awkward. They got a little bit better in C++11, and even better ones will be available in C++17. But we are firmly anchored to C++11, and even though they have improved, using them is really rather cumbersome. And actually, if you look around at a lot of audio code, it's very rare that you see anyone doing anything with custom allocators. But if you were, the general strategy would be that your allocator would allocate a big chunk of memory up front in a non-performance critical bit of your application. And then rather than dialing out to main memory when you need a bit of chunk, you just dip into this pre-allocated pool. There's a slight performance overhead, but it is nowhere near the cost of dialing out to main memory. A much better approach was presented by Louis Dion at last year's CppCon talk, where he was advocating really the ability to use things like the small buffer optimization in almost all C++ objects. It's a much more comprehensive approach. It's super powerful. And if you've not watched the talk, you definitely should, because it is really inspiring. However, you can get most of the benefit of using such an approach with much less effort. And you can do that by just having more indirection. So now your, or at least this function class here it's a bit of a misnomer. So you will not be able to use this function in the same way as you would a stud function. So what happens here is this is a virtual base class, and all the action, everything that I've showed you has just been shifted into derived classes. But the crucial thing here is that these derived classes are free to change the signature. So you can have a templated stack size. Now, if you know the sizes of all the things that you're going to put in your stud function wrappers at the time that you construct them, then you can actually have optimal memory management this way. And you can still put all of these things in a list or in a container because you can use pointers or references to the base class. Benchmarking this against stud function is more tricky though, because you cannot use, well, you can use them in different ways. So if you had a container of stud functions, you would store the stud functions in that container. But with this approach, the lifetimes are slightly different. You store the base class pointers in the container, but the actual objects, these things, need to live elsewhere. Nevertheless, if you do shoehorn them into the same benchmark, you will see that the results are a little ambiguous anyway. Changing the C++ standard, changing the compiler, changing the standard library you're comparing to, will all produce different results. And the upshot is, sometimes stud function is slightly faster than this approach, sometimes this approach is slightly faster. It probably evens out about the same. But this approach, you're guaranteed to not allocate. There is, however, a fairly large elephant in the room, and that is, what if you just don't do any type erasure? So this is the world's least useful function wrapper in that it can only take function pointers. And the only reason that we've created this is to put it into exactly the same benchmark as everything else went through. And if we do that, it's pretty conclusive. Because the compiler can see into the type, it can work out that this entire function just always returns exactly the same number, and we squash down to a single instruction, just return this value. So there is a pretty massive caveat. If you are doing type erasure, then you are telling the compiler that the thing behind this type erasure, you can't know what that is. This is going to be a runtime property. And that can be a pretty significant performance killer. So the caveat is that you really should only use a type arrays callable wrapper if you really don't know the memory layout of the callables that you need to store, or you really need to store different callables in the same container. I mean, there are certainly use cases where you need to do that, but if you cannot do it, then you will probably have a faster program. And a related note is that if you see a stud function in a function signature, then typically, if you instead use a templated type and then just call that type, you will have, your code will run faster. This is because the compiler can see the actual type of the thing that you are using, and so you can get things like inlining. Of course, this does mean that the contract of this function has been blown wide open because there's no constraint on arguments or return types or anything like that. But often the overhead of having really horrible error messages when you try to compile is worse, or at least that's more tolerable than having a slower program. So to conclude, rolling your own version of stud function is not particularly difficult. We've talked about all the real pain points. My code is available, and actually, if you take a hatchet to your favorite standard library, working out what they do isn't too difficult either. And once you've done that, you can replace the internal memory management of stud function with your own scheme. And this lets you do things like enforce real-time safety at compile time by guaranteeing that you're not going to allocate. You can get a modest increase in runtime performance, or you could do something much more adventurous. But the really important caveat is that if you're able to restrict your callable object to those with a certain memory layout or type, then do not use a type erasing wrapper. So that is it. There's a load of information there, and I'll take any questions.
Do you know how the SD14 in place function works? Is it the similar approach to your?
Really struggling to hear you.
What?
Really struggling to hear you. Can you get a bit closer to the mic?
Sorry?
Sorry, it's really struggling to hear you.
Okay, so do you know how the SD14 in place function works?
I think it works in very much a similar fashion to what we displayed there. Okay, so it's effectively this thing, but by itself, without a base class. Sorry, and the session is over and a bit.